In this video, we're going to take a look at a chemical kinetics problem involving rate laws, differential rate laws. In question number 13, we are given a balanced equation where nitrogen monoxide gas reacts with oxygen gas and produces nitrogen dioxide gas. And it was performed at some temperature that's not actually mentioned. There are three experiments that are done where we know the initial concentrations of NO and O2, so we have three trials where we know their concentrations, and where the initial rate of the reaction was measured. There's a fourth trial where the NO and the O2 concentrations are given, where we're going to have to predict what the rate would be. Now, before we jump into the question, notice that the initial rate here has some units that are kind of awkward. It says moles of NO per liter per hour. If we ignore the NO just for a minute, that's moles per liter per hour. Moles per liter is molarity. So instead of moles per liter per hour, we could simply say molarity per hour, and then keep in mind that it does refer to the NO. So the person doing this experiment was measuring how fast the NO was disappearing during the reaction, and their units are molarity per hour. Now let's jump in and see what we're asked for. We need to determine the rate law for the reaction. When you have a reaction with reactants NO and O2 like this, the rate law will look like rate equals a rate constant times the concentration of the first reactant to some power x, which we call the order for NO in this case, times the concentration of the other reactant raised to a different order. The order this time is y. So we're going to need to find x and y, and then we'll have the rate law. We'll also want to know the rate constant. So this k in the rate law is called the rate constant. We'll want to determine it. We'll want to predict what the rate will be in trial 4 as well, and then I might even add one or two extra questions at the end. So let's jump in. If you want to pause the video and see if you yourself can determine the rate law, determine the order x and the order y for NO and O2, go ahead and do that. You might even want to copy the data down so you can do the problem yourself as we go. Alright, so let's jump in. The rate law, as we've said a moment ago, has this form. Rate is equal to a rate constant K times the concentration of the one reactant to the power x times the concentration of the other reactant to the power y. We remember from our factors that affect rates, rate is affected by concentration of reactants, which is why we're looking at the reactant concentrations from our reaction earlier. Let's find x. X is the order for NO. Now, if you're in a math class, you'd probably say that x is an exponent. The term we're using here in kinetics for the exponent in the rate law is to call it the order. So we have the order for NO, we have the order for O2. So x is the order for NO. Now, how are we going to do that? Looking at the data table, what we'd like to do is find two trials where the NO concentration is changing, but where the oxygen concentration, the other reactant, is not changing. So let's see if we can do that. Two trials among these three where the NO is changing, while the other reactant, the oxygen, is held constant. It looks like trials 2 and 3 are good choices. The NO is changing, the O2 stays constant. So for those two trials, we look at their rates, and we notice that rate number 2 is larger than rate number 3. So what I'm going to do here is use trials 2 and 3, where the NO concentration changes, but the O2 concentration is constant. And we just saw that rate in trial 2 in this case is larger than rate in trial 3. So I'm going to take the rate for trial 2 and divide by the rate in trial 3. I strongly suggest that you always divide the larger rate on top by the smaller rate on the bottom. So using the numbers from the table earlier, the rate in trial 2 was 6.8 times 10 to the minus 8 molarity per hour, divided by the rate in trial 3, which was 1.7 times 10 to the minus 8 molarity per hour. Now before we actually evaluate that, let's do something a little different. Notice in our rate law that rate is actually equal to this, K times NO to the X and O2 to the Y. So the rate here on top, rate number 2, has to equal K times the concentration of NO to the power of X and concentration of O2 to the power of Y. Similarly, on the bottom here, the rate number 3 is equal to K times the concentration to the power of X for NO and the concentration to the power of Y for the O2. And of course on top we were referring to trial 2, so look at your table and grab the concentrations from trial 2 and plug them into those brackets. In trial 2 the NO's concentration was 3.6 times 10 to the minus 4. In trial 2 the O2 is 1.04 times 10 to the minus 2. Similarly in trial 3, 1.8 times 10 to the minus 4 was the NO concentration, and the O2 was the same, 1.04 times 10 to the minus 2. Now notice, because we kept the O2 concentration the same, something interesting happens here. The O2 concentration, 1.04 times 10 to the minus 2, to the power of Y, cancels on top and on the bottom, because it was held constant. Similarly, the rate constants also cancel. So let's see what we have left. On the left side of that statement, 6.8 times 10 to the minus 8 divided by 1.7 times 10 to the minus 8. If you grab a calculator, you'll see that that equals 4. On the right-hand side, 3.6 times 10 to the minus 4 to the power of X divided by 1.8 times 10 to the minus 4 to the power of X gives me 2 to the power of X. All I did there is take the numbers and I divided them to get 2, and because the numbers were raised to the power of X, 2 is raised to the power of X as well. Now when you look at this remaining statement, 4 equals 2 to the power of X. If you think through some simple powers of 2, 2 to the power of 0 is not equal to 4, it's equal to 1. 2 to the power of 1 is not equal to 4, it's equal to 2. 2 to the power of 2, hey, that's equal to 4. So the X here has to equal 2. So we'll say that the NO is second order because its order was a 2. So NO is second order. Now we'll find Y. Y is the order for oxygen in our rate laws. Use the same logic that we used a moment ago. We want the oxygen, 2 trials where oxygen is changing while the other reactant, in this case the NO, is held constant. Let's see. Are there 2 trials where oxygen is changing while the NO is held constant? Well, if you look at trials 1 and 2, the O2 there is changing while the NO stays constant. So let's see what we get. We'll use trials 1 and 2. The O2 changes, but the NO is constant. Now if you are able to find 2 trials like this for the second thing in your rate law, then it's probably best to do it, as we're about to do here. But I'll show you in a moment that now that we know that X is a 2, the requirement that the other reactant stay constant is no longer true. We're able to find the second order, in this case the Y value, even if the NO was not being held constant, because we already know the NO's order. I'll show that in just a minute. But since we had here two trials where the NO was being held constant, it's just easiest to use that. So we looked at the rates in our table for rate 1 and rate 2, and we noticed that rate 2 is the larger rate. Rate 2 is larger than rate 1. So I'm going to take rate 2, the larger rate, and divide by rate 1, the smaller rate. And using the numbers from the table, 6.8 times 10 to the minus 8 molarity per hour divided by 3.4 times 10 to the minus 8 molarity per hour. And as we did before, on top, that rate there has to equal K times. Now earlier we said NO concentration to the power of X. However, we now know that X is a 2. So let's not put an X, and we'll just put a 2. Times the oxygen concentration, whose order we're still trying to find, so for that one we'll say to the power of Y. And then on the bottom, K times NO concentration squared, and oxygen concentration, again to the power of Y. Using your table, find the concentrations in trial 2 and put them in the brackets on top. So on top we have 3.6 times 10 to the minus 4 for the NO, and 1.04 times 10 to the minus 2 for the oxygen. In the denominator, do the same thing from trial 1, and there we had 3.6 times 10 to the minus 4, and 5.2 times 10 to the minus 3 as the concentration of oxygen. Now, because the NO concentration here was constant, this term simply cancels. The rate constants also cancel again, and when we divide on the left side, this time instead of 4, we get 2. And on the right side, 1.04 times 10 to the minus 2 divided by 5.2 times 10 to the minus 3 is also equal to 2, but it's raised to the power of Y. So 2 to the power of Y. And then, thinking again of those powers earlier, 2 to the power of 0 was 1, 2 to the power of 1 is 2. Since we have 2 to the Y is 2, we can see therefore Y must have been a 1. 2 to the power of 1 is 2. And now we would say that the oxygen, the O2, is first order. Okay, first order. First order because its order was a 1. The overall order of the reaction, in this case, would be a 3. If the NO was second order, while the O2 is first order, you get the overall order for the reaction by adding those orders together. So the overall order for this reaction is 3. It's third order overall. Now I've hinted a moment ago that we actually didn't need the NO to stay constant, since we already knew the NO's order in the first part of this question. Let me just show you what I meant by that. If you look back at your table, notice we had used trials 2 and 3 in the first determining the value of X. What if we used trials 1 and 3, where the O2 is still changing, but now the NO is also changing? Let's see what happens if we do that. We need the O2 to be changing, since we're trying to find the O2's order, but what if the NO had not been held constant? Let's use trial 1 and trial 3 and see what happens. Again, let's take the larger rate, divide by the smaller rate. So we're going to use trials 1 and 3, and for those two trials, trial 1 had the larger rate, so rate 1 divided by rate 3, and we would have had 3.4 times 10 to the minus 8 divided by 1.7 times 10 to the minus 8 equals, on top we'd have K times something squared times something to the Y, and on the bottom K times something squared times something to the power of Y. Now if we use the concentrations in trial 1, we'd get 3.6 times 10 to the minus 4 and 5.2 times 10 to the minus 3. And on the bottom for trial 3, 1.8 times 10 to the minus 4 and 1.04 times 10 to the minus 2. Now what happens here when we divide? On the right, the only thing that's the same on the top and the bottom now is the rate constant, so it's the only thing that cancels. Now let's do the dividing. On the left, 3.4 times 10 to the minus 8 divided by 1.7 times 10 to the minus 8 gives me 2. On the right, 3.6 times 10 to the minus 4 divided by 1.8 times 10 to the minus 4 is 2, but that 2 has to be squared, so let's put to the power of 2. And then on the other thing is 5.2 times 10 to the minus 3 divided by 1.04 times 10 to the minus 2. Now when I do that on my calculator, it gives me an answer of 0.5. But if I write that as a fraction, it would be 1/2, and it's raised to the power of y. You can see this is not quite as nice as before. But notice we have here 2 squared times 1/2 to the y. We can divide both sides by 2 squared to move it away from the right-hand side. 2 squared is 4. So 2 divided by 2 squared, 2 divided by 4 is 1/2. And on the right, 2 squared divided by 2 squared cancels. And we're left with 1/2 to the power of y. And now 1/2 to what power gives you 1/2? The answer is the same as before. Y is still equal to 1. So notice that because we had determined already that the NO's order was a 2, we could evaluate what 2 squared equals. It equaled 4. And then we could just divide both sides by that to get rid of it on the right-hand side, and we're left now with a term that has just y in it. So when you've already determined one of the 2 orders, or when you're down to your last order, put it that way, you don't have to have trials now where that where everything is held constant except the thing you're looking for. I'll stop there because I'm starting to sound a little confusing, I bet. So there we found the value for y in 2 different ways. We could now say the rate law. The rate equals k times NO to the power of x, and NO to the power of 2, and O2 to the power of 1. Because it was to the power of 1, you could have just left that out and said NO squared times O2. Okay? So rate equals K times NO squared times O2 would be equally valid. Part B, we want to find the rate constant for the reaction. And I'm going to do this a little bit quicker, I hope. We've got 3 trials where we have data, and this is all fake data. It works perfectly in our calculations. We're going to choose just one of them and find K for that trial. If it were real data from an experiment, you'd have error involved, and so what you would do would be to calculate K for each of the 3 trials, and then find the average value of K. Since this is fake data, it's working perfectly, we'd be wasting our time to calculate K 3 times because it would be exactly the same in each trial. So let's just do it for one of the 3 trials. We're going to find K, and I'll do it for trial 1. If you'd like to test me and you try it for trial 2 or trial 3 and see if you get the same value as I do. From the rate law, we can rearrange that statement and say that K is equal to the rate divided by concentration of NO squared and the concentration of O2. Now let's take the information from trial 1, and the rate there was 3.4 times 10 to the minus 8 molarity per hour. Notice that I'm now putting the units in. Really important to remember that. When you're finding the rate constant, you must put the units in and include the units with the value of the rate constant. You will definitely not receive full credit if you leave that out. So on the bottom, we have to have NO's concentration squared and O2's concentration. So from trial 1, 3.6 times 10 to the minus 4 molarity, and on the O2 concentration, 5.2 times 10 to the minus 3 molarity. Grabbing our calculator, we can divide this in a couple of ways. I'll show you the way I like to do it on my calculator. I like to take whenever I have things like this on the bottom that are multiplying, I like to divide twice. I'm going to take the numerator and divide first by this term and then by this term. That's because they're multiplying on the bottom. So let's try that. 3.4 times 10 to the minus 8 divided by 3.6 times 10 to the minus 4 squared, and then also divided by 5.2 times 10 to the minus 3. And that gives me 50.45, but I'm going to keep just 2 digits because these numbers all have 2 digits, so I'll say 50. Now another way you could have done that would have been to type 3.4 times 10 to the minus 8 divided by. If you don't like to do the dividing twice, then now open a pair of brackets and simply type the bottom part of your fraction in. So 3.6 times 10 to the minus 4 squared times 5.2 times 10 to the minus 3. Close your bracket, equals. And notice you get the same answer, 50. Now, the units for the rate constant are really important to include with the answer. Let's see what we get. On the top, we have a molarity per hour. On the bottom, we have molarity squared times molarity to the power of 1. M to the 2 times m to the 1 gives me m to the 3, right? Using grade 9 math, you add the exponents when you're multiplying powers with the same base. Now we're going to divide powers that have the same base. M to the 1 divided by m to the 3 is m to the power of minus 2. When you're dividing powers with the same base, you subtract their exponents. So 1 take away 3 is negative 2. And then we have the per hour also. So there's the value of K with its correct units, molarity to the minus 2 and then hours to the minus 1. Part C said to calculate the rate in trial 4. So let's find the rate in trial 4. We now have a rate law which says K times NO concentration squared and O2 concentration. And we know that K is 50, and we know in trial 4 that the NO concentration was 1.8 times 10 to the minus 4 squared, and the O2 concentration there was 5.2 times 10 to the minus 3. With your calculator, you can type that in and evaluate it. What you'll find, let's just quickly do it, is 50 times 1.8 times 10 to the minus 4 squared, and then multiplied by 5.2 times 10 to the minus 3, and we get an answer of 8.4 times 10 to the minus 9, and since it's a rate, it'll have the same units as was in the data table, molarity per hour. There's our rate in trial 4. Now let me just quickly add one last question. This wasn't on the original paper, so question D. What was the rate of disappearance of O2 in trial 1? Let's take a look back at the table. In trial 1, the rate of the reaction was given as 3.4 times 10 to the minus 8. But notice that was rate based on the NO. The person measuring this rate was measuring the rate of change of NO. The question now is asking us what was the rate of change, the rate of disappearance of oxygen instead. Well, let's write that balanced equation down. 2 NO2s reacted with 1 O2 and made, 2 NOs reacted with 1 O2 and made 2 NO2s. We know that the rate In trial 1, based on the NO from our table, was 3.4 times 10 to the minus 8 molarity per hour. What's the rate of change, the rate of disappearance of the oxygen in that trial? The key is to look at the coefficients. Every time 2 moles of NO disappear, only 1 mole of O2 disappears. So the O2 is disappearing 1/2 as fast as the NO. So if the NO was disappearing at this rate, the O2's rate of disappearance would be 1/2 of that because of the ratio of the coefficients. So that's going to be 1.7 times 10 to the minus 8 molarity per hour. What if the question had asked us about the rate of appearance of NO2? Well, notice there that its coefficient is also a 2, just like the NO. So 2 to 2, every time 2 moles of NO disappear, 2 moles of NO2 will appear, so its rate of appearance is the same as the rate of a disappearance of NO. It's a 2 to 2 or a 1 to 1 ratio, so its rate would be the same, 3.4 times 10 to the minus 8 molarity per hour. So we were given the rates in the table based on the disappearance of NO, and we can calculate from that the rate of disappearance of O2 or the rate of appearance of NO2 simply by looking at the ratio in the balanced equation. So there's a typical rate law problem with multiple parts to it that are all reasonable and very common in this kind of question. Be sure you're well prepared with this topic because it's definitely going to be a question on your test and on your final exam. Good luck.